Now the simple exponential smoothing model, which we will be referring to as SES, is also called exponentially weighted moving average. And that's because if you look at the formula, what we're trying to do here is to compute a kind of an average value for the time period t, at the end of time period t, and we're trying to compute an average value for t plus 1. And for that, we take the values y sub t, and then y sub t minus 1, the one previous to that, previous to that, and previous to that, and the weights that we apply will be like this. Okay? And if you go through the formulas and do a backward substitution, you will see that the weights will come out to be these. Alpha, then the one previous to that will alpha times 1 minus alpha, and then alpha times 1 minus alpha squared, then alpha times 1 minus alpha cubed, and so on, all the way up to the first value y sub 1. So if you plot these with time on the x-axis and the weight and on the y-axis, then this is what you will see. So it's the time lag in the y-axis and the weight. This alpha times 1 minus alpha to the power of t. And you see the weights as the lag, as you go farther and farther back in the past, the weight applied to that particular y value declines in an exponential fashion. So smaller the alpha value, the less steep the decline is. It's more stable. Larger alpha value, the decline is pretty fast. Okay. This is the reason why, since the weights are exponentially declining in the past, this method is called exponentially weighted moving average. The weights are exponentially smaller and smaller as you go way back in the past. So if you take that formula and apply it, so when we use L sub t as the forecast for the next time period t plus 1, then forecast for t plus 1 will turn out to be f sub t plus alpha times the error in the period that just ended. So if you take what the forecast was for time period t, and to that you add alpha times alpha being a value between 0 and 1, a portion of the error. Okay, and the alpha value must always be between 0 and 1, and this is called smoothing constant. Now there are a couple of things that are important here. One is, what should be the value for alpha? What is the best value for alpha? Okay. What we will do is we'll start with an initial trial value. We just make up a value and then figure out what the best value is going to be for our data. And also we need a first forecast, a forecast for the very first time period. Okay. And how do we come up with that? A couple of ways in which we can come up with the initial starting value for the forecast. One is to use the very first actual y value as the starting value for f, or we can take an average of the first few observations and use that as a starting value for the next time period. So now let us go to the Excel file and set up this example. Okay, so here is example 3.1. Here is the sales data for 12 time periods, and let's set up an alpha value of 0.3 as our initial value, and let's assume the initial value for the forecast we'll take the actual value for the first time period and use that as the forecast for the second time period. Okay, f sub 2 is y sub 1, and that's how we are defining, that's how we're going to start the simple exponential smoothing process. And we can define this differently in different problems, so you have to pay attention to that. How are we supposed to start our initial forecast? Don't assume that this will always be the case. In this example, we have defined the initial value as the first forecast for time period 2 will be the actual value from time period 1. Then the error would be the actual value minus the forecast. Okay, so the forecast for the next time period will be, so you take the previous forecast plus alpha times alpha. Here is alpha, which we have just we are using 0.3 as our initial trial value. Now that alpha must always come from that cell B5, so we have to absolute reference that times the error value. Okay. So now we copy that error down here. Now let's get rid of the underline. We don't want that. Okay, well, we want the underline there. Put that back. So now we copy these two all the way down. Let's format these numbers to say 2 decimal places. Put the border back. Okay, so now if you copy that one more time period, so that would be our forecast for time period 13. Now that's our forecast using SES, simple exponential smoothing. And what about the errors? So let's look at the error computation. Remember, we're going to be using the functions, but just for this sheet alone, I'm going to use both the function and the initial principles of finding the forecast error. So we'll start with period 3. Okay, we'll skip the first period because the first period is initial time period, so the error is not strictly an error. So we're going to start computing the forecast error starting from period number 3. So error squared. Okay, now absolute error then absolute error divided by the actual value. That will be absolute percentage error. Okay. Copy these down there. Let's format these, make sure that all the numbers are properly formatted. Okay, so now if you do an average of these, okay, so you get ME. Okay, and then we copy that. So here is ME, this is MSE, mean square error, this is mean absolute error, MAE, and this is mean absolute percent error. Okay. So ME, there is no function, I don't have a function for ME, so it's just that. Now I'm going to use the functions that I have developed, and this is available in your shell file if you had enabled macros, enabled content. So when you type MA, you should see all of these different function names prompted. If you don't see the function names prompted, that means you don't have the functions enabled. Okay, so now we're going to compute from t equal to 3 through 12. So the actual sales and the forecast. Y range, comma the forecast range. And that will give us MAE, so which is that. Okay. And then MAPE is MAPE, again, the actual sales and the forecast. Okay, MSE, again the same, actual sales and the corresponding forecast. Okay, or MSE, root mean square. Okay, root mean square, you can take square root of MSE also. You don't have to use this function. Okay. Now MAPE is a percentage, so let's make that into a percentage. Okay, let's reduce the number of decimal places here. Okay, MASE and Thiel's U, remember these two are comparative measures with respect to random walk. So MASE, you have to give three things here. Okay, one is the actual values, comma, the forecast that you're considering, comma, the random walk forecast. Random walk forecast would be whatever value was the previous actual value becomes the forecast for the current actual value. So the forecast for random walk would be the actual values starting from time period 2 through 11. Time period 2 through 11 actual values will be the forecast for time periods 3 through 12. So give that. And remember from chapter 2, any value greater than 1 means the random walk is better than the current forecast you're considering, forecasting model you're considering. Any value less than 1 means the forecasting model you are considering gives you smaller error than random walk, and therefore it's worth considering. So any value that is greater than 1 or greater means you might as well use the simpler model and get even smaller error, or at least the same error like the model that you're considering, the simpler model being the random walk. Now Thiel's U, okay, again the same concept. The actual value, the forecast you are considering, comma, the random walk forecast, which is actual time value starting from time period 2 through time period 11. And the Thiel's U is even larger. So this tells us that the simple exponential smoothing is not giving you, with alpha equal to 0.3, is not giving you better forecast than random walk naive model.